Okay, guys, let's go. I'm recording. So, Unit 10 is chemical bonding. This is going to be, we're going to talk about shapes, Vesper. We're going to talk about energies, the types of bonds, and we're going to talk about hybridization and some other stuff that you haven't seen before. So, some questions that we're going to consider is what is meant by a chemical bond. So, when you hear chemical bond, what's that mean? Two what? Atoms bonding together? Okay.
Not by physical means, but when their ions join.
They're sharing electrons.
Yeah.
Sharing electrons, or we can transfer, donate. Okay. So why do we form these bonds?
For drugs.
To be stables. They want to be happy. So what happens to their energy when they form bonds? The energy decreases, yes.
They're stored in the bond.
Okay, so those are some things that we're going to think about as we go along. So one thing is you can see here's the interaction of a hydrogen atoms as they fall apart, or as they're far apart, and when they're far apart they don't interact with each other, but as they get closer together they start interacting a little bit more, and then they will form that bond and achieve that lowest energy that they want to be at. So just looking at that and seeing that how they are moving closer together. As they move closer together, they get more interaction. So some keys that we're going to talk about is one, ionic bonding. So these are electrons, where our electrons are transferred. And how are these bonds, how are they bonded? If we're exchanging electrons, what's holding these atoms together? How are they held together? Forces. What type of forces? Positive and negative. So it would be electrostatic forces. Okay, so they're held together by electrostatic forces.
That's for the ionic bond?
For ionic bond, yes. Now in covalent bonding, what happens is this is going to put non-covalent on top, non-polar covalent. So these electrons are shared equally by the nuclei. So if I were to, I've lost my meter stick. If I were to have my meter stick and I were to hand it to here, and we just hold it, we have a bond and we're equally sharing, okay? And that would be our non-polar covalent. But what we have is an intermediate case, which is our polar covalent bond. So this is very huge in the AP world. Polar covalent means that it's an unequal sharing of those electrons. So here, if I bond with America again, and America becomes more electronegative, then which way are they going to pull? It's going to pull more towards America, and she's going to be hogging the time with those electrons. Okay? So what we have is a charge separation, and we will call this a dipole moment, and I'll talk more on that tomorrow. And your homework tonight is A. So a dipole moment, so what happens in a dipole moment? So if we have here hydrochloric acid, who's the more electronegative one? Chlorine. So what happens is chlorine gets a partial negative charge, and hydrogen becomes partial positive. Now we don't give these numbers, we just say it's a partial negative or a partial positive. So you might see it written like that with the delta negative or the delta positive, but we will also write it with an arrow pointing going towards the atom that is more electronegative. And then what we're going to do here is we're going to put a little line down there. That means that's where the positive part is. Okay? So you will see these different ways. But that means that chlorine is the most electronegative. Any questions on that? Okay. So electronegativity, again, this is just review that this is the ability of an atom to attract electrons to itself. If we go back to the last unit, we know that the tendency of electronegativity is to go up and over to increasing our electronegativity, with which one being our most electronegative atom? Fluorine. Okay. So all these have values on the periodic table. We looked at these last year, or you should have, or the year before. We've looked at these values, and we were able to put these values, those differences of those values, into whether it was ionic covalent or polar covalent or non-polar covalent. So if you will see here, this is where we're talking about those values. And what you need to know is that if I'm looking at these and I see these values, what we talked about last year was like anything less than something was nonpolar, anything greater than 1.7 was ionic, and in between there was, anything less than 0.3 was nonpolar, anything greater than 1.7 was ionic, and anything between was what we said was polar covalent. What we're going to do here is, first of all, an ionic bond is between what? We're going to base ionic bonds on what type of elements they compose them. So what composes an ionic bond? Metal and nonmetal. And we know that covalent bonds are two nonmetals. And then what we're going to do is we're going to further classify these into polar covalent and nonpolar covalent. So in the AP world, we're not using any of these values or whatsoever. If an atom, so all bonds are polar covalent unless they have equal electronegative values. So we are all polar unless we have equal electronegative values, then it is nonpolar. So what kinds of things have equal electronegative values? I bring clay for our new house. So those types of bonds, a chlorine, chlorine, fluorine, fluorine bond is nonpolar. All other is either going to be ionic or polar covalent.
So diatomic.
So diatomics. Mm-hmm. Any questions on that?
What about like BH3?
Okay, so if you're looking at you said BH3? So if you're looking at B and H, that would be a covalent bond, polar covalent between each B and each H, but the overall molecule would be nonpolar. Okay, so you look between the bonds, and then you have the overall molecule. Okay, so let's look at these concept questions. If lithium and fluorine were to react, which is more attracted for an electron and why? So who's going to take the electron and why? Fluorine. And why? It's the most electronegative. And why is it the most electronegative? Just to add on that. Because, You can't say because that's the trend.
I never said that.
I know, but if we look where lithium is and fluorine is, they're in the same period. So what would be affecting them? Shielding or nuclear charge? Nuclear charge. So it has a larger Zeph. Okay. Now, if we looked at fluorine and iodine, which one would have more attraction for an electron and why? So fluorine would be the more electronegative, because it's more electronegative, and then why in this case is it more electronegative? It has less shielding. And then let's go back and classify these. Lithium and fluorine is what type of bond? Ionic. And if we have fluorine and iodine, it would be polar covalent.
Polar covalent?
Mm-hmm.
Because it's part of the diatomic.
They're not the same atom. Question?
But they're in like the go to 7, make to 7.
They're both diatomic,
Okay.
but when they're together, they won't. They're not diatomic. Does that make sense? Okay. Okay, so more exercises. Let's arrange these bonds from the most to the least polar. So the most polar is going to be the ones that are further apart on the periodic table. So if you're looking at the periodic table, who would be our most polar in this group, first group? CF. So CF is more polar than what's next? NF. And that is more polar than OF. Okay, so those are all looking at fluorine compared to fluorine. Let's look at some other ones that are real different. So which one here would be the most polar? Looking at the periodic table. Silicon and fluorine is greater than, which would be next? Carbon fluorine. And next would be NO. And lastly, here, who was the most polar? BCl. And then we have SCl. And then ClCl. And this is the first time we've actually seen a true nonpolar.
I have a question.
Uh-huh.
What if it was saying which one is most to least polar and like it's further apart on the periodic table? So like if it was, for example, argon and potassium, would those be closer than argon and phosphate? Or phosphorus, I mean? That is phosphorus, right? Like the P and the AR, are those closer or is argon and K?
I would say that P and AR would be closer.
Okay, so you wouldn't count like. Is it just
Because we're not pulling it all together.
Okay.
Like one big, if they were in the lines next to each other, you wouldn't look at, you'd still look at their characters. How K is a +1, whereas you have phosphorus is a non-metal. So if we had K and say Cl or argon, then that would be a ionic, whereas the P would make it a covalent. Because you have to look at the character too.
Okay.
What's the character look like? Okay. Now, if you were to looking at F, fluorine, and you said had O and S, then S would be more polar than the O because it has an extra shield than the O does. Okay. All right. So next. We've said that any compound that conducts an electric current is ionic when melted. So these come together via electrostatic forces, we've said. So what we're going to talk about today is Coulomb's law or lattice energy. And you read about that yesterday. in the POGL. So this is when those two ions come together, they form a crystal. And that crystal is called a lattice. So here if I have sodium and chlorine, and this is, say, a salt crystal, this is what it looks like. It makes this nice little lattice. Everybody knows what a lattice is, right? Okay. So we have the nice little crisscross thing. So it makes a lattice. And the energy that is released when these come together is called the lattice energy. Going back to physics, you may also see this called Coulomb's law. Okay, so we're going to use those interchangeably. Questions? Everybody good? Okay, next. So here is the equation. So lattice energy is equal to this constant times QQ. So Q is our charge. And we're going to multiply those two charges and divide it by our radius. So I'm just going to write under here Coulomb's law. Again, you may see it like that on the periodic table or on the AP exam. So QQ, and we just charges, we're dealing with AMUs, so I just want +1, -1, +2, -2. We're not going to have these big values. We're actually not even going to solve for these values. We're just going to look at them and kind of look at the comparison between these types of atoms rather than solving for the actual lattice energy. But you need to know that the more charge that the atoms have, so say a +2 and a -2, the more charge you have, then you're going to have a larger lattice energy. Which makes sense, you're multiplying those two numbers together. Now, if you have more radius, so you have some large atoms, then what's going to happen to our lattice energy is it's going to become smaller. So if you think of the meter stick, and we take it and we have this huge meter stick and we break it, it's going to take not very much energy. But as we start going in further and breaking it in half, breaking it in half, breaking it in half, it's going to get harder and harder as the pieces get smaller. Okay?
Are they going to give us the radius?
I would say they're not going to, if they asked you to calculate it, then yes, but I would say you would be looking at the periodic table and kind of bigger. If you have a huge QQ over a large radius, then that lattice energy is going to be small when you divide it, okay? So it's kind of all a little relative. So here is, if we look at this and we see our electronegative difference, if there's zero difference, then we know it's a nonpolar covalent bond, which means it has high covalent character, and its ionic character is low. And then as you go down the chart, you see polar covalent, and then you have, if you have a large electronegative difference, then it's going to be ionic, which means it's going to have high ionic character or low covalent character. And when I talk about character, I'm talking about like properties, that type of stuff. Any questions on that? All right, 2 more slides and we're done. All right, next. Calculate the bond type based on the character above or the chart above. Order the set from the most covalent to the most ionic. So the first thing I want to do is just let's go through there and say, is it ionic or covalent? So the very first one, NaCl, what type of bond is that? Ionic. And we know since it's ionic, we can do Coulomb's law, so QQ over R. We know we have a +1 times a -1. And we don't know the radius, so we're just going to leave that alone for right now. What about lithium hydride? What type of bond is that? It is ionic. We have a metal and a nonmetal. In this case, we know lithium's a +1 and hydrogen is a -1. Okay? And again, we don't know the radius, so we'll come back to that. But we do know that both their charges are the same. HCl is what type of bond? Covalent. Polar covalent, yes. HF, polar covalent. And BeO. It's ionic, and what are their charges? We have a +2, -2, so we have a really huge charge there. Okay, so very first thing, let's go ahead and say what is our most covalent character? So we have C and D. Who's more polar covalent? Polar covalent means they're further apart. Which ones are the further apart? HCl. So C has, so I'm going to put here that it's more covalent. So C, and we're going up to ionic character. It's greater than D. Now let's go to the ionic ones. And so we see BeO has that huge charge over there. So let's go ahead and go to the smaller charge ones, because the smaller charge ones are going to be in the middle. Yes?
You wrote C is less than D.
So I'm going from most covalent to the most ionic.
Okay.
So does that make sense?
Yeah, you just said C is greater.
Oh, sorry. Well, it's more covalent, but it's less ionic. Yes. Yes. So I'll write that here. So if anybody less ionic. Okay. So looking at the two ionic ones up there, the NaCl and the Li, their charges are the same, but let's look at the radius. So who has the smaller radius? Looking at the periodic table. Li and H has the smaller radius. Whereas if we have NaCl bonded together, then it is bigger. So when we divide these, then which one is going to give us the smaller number? A. So that means it is more covalent than B is, or less ionic. And then if we look at BeO, we see that Be and O, they're what'd you say?
They have a smaller radius than NaCl.
They do have a smaller radius than NaCl, but they have a larger charge. So it would be our last one. It would be our most ionic. Okay? Now, what I will say is that on the AP exam, they're not going to give you something like this. They are going to either keep your radius or your charge constant. They're not going to give you something where it's all flipped around. Okay? Okay. So lastly, number 5, what classes of elements typically unite to form compounds that contain ionic bonds? Metals and nonmetals. What else are there? Not metalloids, metals and nonmetals. What would we say about NaNO3? What is that? Metal and a polyatomic ion. And lastly, I would say, what about NH4NO3? What would that be? It's an ionic bond, but it's between what? A polyatomic. So you can have a polyatomic and a nonmetal, or you can have a polyatomic and a polyatomic. What's the only polyatomic that we have? Positive polyatomic. Ammonium, NH4. Okay, and lastly, this question number 6 is a old AP problem. It says, explain the magnitudes of these lattice energies in terms of ion sizes and ionic charge. So the very first thing I would do is something like this. I would say lattice energy is equal to QQ over R. And then go to my problem, and what is staying constant? K staying constant, so that the charge is staying constant too. Okay, so Q is staying constant, so we care about R. So explain to me why KF has a higher lattice energy than KI. Smaller radius. So KF is largest because the radius is the smallest. Questions on that? So there you go. That's it.